Hello, learners. Today, I will tell you about the decision-making statements in programming with decision-making statements. Decision-making structure, program structure, is also called the selection logic structure. I will share you my slides to make the lecture more vivid, better understandable to you. So let me give me a few seconds to share the screen. First, I shall tell you about the objectives of this lesson. This lesson is meant for illustrating another fundamental logic structure known as selection logic, which shows how to write statements for decision making. In most of our everyday procedural works, we need to take a decision for more action. There may be a number of alternative actions based on some condition. We illustrate here how to write such statements in an R program. The task of selection is basically the task of decision making. Here, a condition or conditional expression is checked for its truth value. If it is found to be true, a set of action statements are stated for execution. Otherwise, that is when it is found to be false, an alternative set of statements may be specified for execution. The specification of this alternative set of actions is not always necessary. If it is not mentioned, then the following statements are executed according to the basic principle of program execution in a computer. A statement with the selection structure is also known as a conditional statement. Using the symbols of flowcharts, the selection logic of program development may be depicted as shown in the figure below. This start symbol implies what? Just before the acceptance of inputs, with which is selection will be performed. There may be some inputs, there may not be any inputs. Some assignment statements may also be written here. After that, on the basis of the assigned values, we can check some condition. P is also called a predicate. If the condition is found to be true, we write the statements here, which we call here actions to be taken. Statements are written one after another. If it is false, we write the statements to be executed one after another. So actions to be taken if the condition P is found to be false. And this completes the selection part. Here, that's why I've shown here the end. It may not be the end of the program. After that, some output statement may be there or some other statement may be there. But as far as selection logic is concerned, this is the main part of the selection logic structure. So let me explain it further. Here, P is the condition to be checked. It is formally called a predicate. Provides with the following syntax for a selection statement. If P, then we start a brace. And in the next line, we write action statements for true value of P, and we close the brace. If there is an else part, we again start with the brace, and we write the action statements for false value of P. And that is if P is not true. The use of else part is optional, as I've told you earlier also. If there is a single statement in each part, then the pair of braces is also optional. Example 3.1. 3.1 implies what? It is the first example of lesson 3. Price, we assign 500 to some identifier variable price. And next we can check price in this way. If price is less than 100, suppose the discount is 10% of the price. So we can write the statement in this way. Discount assignment operator is equals to what? Price into 0.10. This generates the 10% of price and puts the calculated value in the variable discount. Else, otherwise we calculate the discount. That is, otherwise means if price is not less than 100, that means if it is greater than equals to 100, suppose the discount is 15%, assuming the discount to be 15%, in that case, we write here price into 0.15, and the discount thus calculated can be stored in some variable, say discount. Here the variable is same. Discount is either calculated using this condition and using this calculation rule, or using this calculation. And next part is what? It is the end of the selection logic structure, end of decision-making statement. Now we may like to show the output. So we can show the output in this way. The discount will be discount for price equal to price can be shown, then a new line character. We can use if within if any number of times. Such a structure is called a nested if structure, and the following example illustrates the use of nested if statements. Example 3.2. Suppose P is a variable that contains 18, Q is another variable where we assign 15, R is another variable where we assign 9. Now we can check in this way: if P greater than P, these values can be accepted as input from the terminal, as we showed the input statement in the earlier preceding section, preceding lesson. So we can check in this way: if P greater than Q, if it is true, then if Q is greater than R, if it is also true, then we get the largest value, and in the location largest, we assign the value of P. P happens to be the largest value. Else, this else part is what? It is the else part of this if, second if. If P is greater than Q, but Q is not greater than R. If Q is not greater than R, it means what? Largest value is R, because P is greater than Q, Q is greater than R, then we have to check, of course, we have to check if P is greater than R. If it is that, largest value will be P. Else, this else part is actually the else of this if, last if. Else of immediately if above, and otherwise largest will be R. Then another else. This else means what? This is the else part of the first if, because the else part of this if was here in the second, in the first else. So this else is if, it means what? If P is not greater than Q, then what to do? Then we need to check if P is not greater than Q. That means what? Q is greater than P. So we need to check whether P is greater than R or not. If Q is greater than R, we can conclude that largest equals to Q. Else largest equals to R. Now we can print the largest value. It may be noted that in case some else is followed by if, then no braces are allowed after that else. Multiple conditional statements in R. Another form of the conditional statement may be the checking of multiple conditions one after another. And this is used when we need to check another condition. If the preceding one happens to be false, it takes the following structure. Checking of multiple conditions takes the following structure. So if condition 1, then statement set to be executed. If the condition 1 is satisfied, then this statement set will be executed, and control will go out of this whole if else statement. Otherwise, next condition is checked. If it is found to be true, then this statement set 2 will be executed, and control will be out of the conditional statement. Else, in this way, if else can be continued any number of times, where m is an integer. So we write condition m, statement set m to be executed, where m is any whole number. Otherwise, a statement set n to be executed. So any one of the statement sets will be executed. Not more than one statement set will be executed in this case. It may be noted that any one of the above n statement sets will be executed for a given set of values. It is because the conditional expressions are mutually exclusive. That is, if one conditional expression happens to be true, none other predicate can be true at the same time. The decision-making statement stated above can also be written in a single line as shown below. If P statement to be executed, After that, if the conditional expression is P is true, else statement to be executed if P is false. So we can write in a single line also. Hence, the conditional statements in example 3.1 can be rewritten as follows. Price equals to 500. If price greater than 100, discount equals to price into 0.10. Else discount equals to price into 0.15 and semicolon. And we write the discount will be this, discount price will be this, for price will be this, and we will get the result. And let us check this, check the execution of this statement in our environment. So we copy this line so that we need not write it and go to our environment, go to install, go to load R actually. Here is the R icon on the desktop. So we load R. Just a few seconds. R has been loaded. So let us copy this here, paste this here, paste the copied statement. No, it has not been copied correctly because two statements are here. First statement was executed and next statement is this. So we want to copy this in a different way. This cannot be executed. First one was already executed. So this cannot be executed because the codes are here copied from a PDF file. So the codes have to be changed. We change the codes, then we can get it executed. Let us change the codes. These are quotation sign from PDF file. The codes are different for R here. So we change this. The previous statement gave no error, so it has been executed correctly. So let us execute this now. The discount will be rupees 50, will be 50 for price equals to 500. Let us write both the statements in a single line. Copy. Then we write this. You see? So you can write a number of statements in a single line also. Now it has been written, if price is greater than 100, discount is 10%, else discount is 50%. Actually, it has been written here in a reverse way. That is not correctly written, correctly depicted that logic. So let me rectify it. We rectify it, copy without the ending parenthesis, so we copy it here. Now we change the greater than to less than sign. Originally it was less than. If price is less than 100, then discount will be 10%, else discount will be 15%. So discount will be this now. So let us close the parenthesis and enter it. Now the discount, you see, discount is 15% of the price, because when price is 500, the discount should be 15%. So this is how we can execute a number of statements. You see, simple assignment statement is executed. Decision making or conditional statement is executed with if else, and output statement of else cat with the cat to show result is also executed. Can also be written in the same line. So we get all the statements executed in a single go. Okay, let me return to the presentation. Okay. It was greater than here, but somehow it became less than, I don't know. Okay, I have changed it and I've got the correct result. So the nested if can also be written similarly, you see. Suppose these are the values, P, Q, R. We write this as a statement without taking any input. We write this as a statement. We could have taken inputs also. So let me write these statements, PQR, the value of PQR. Okay. So assignment is done. So now we write the single statement with if else, you see. Let me copy this whole part. This up to this I have copied. Copy this up to else part. Now still there is something. Put a space and again go back. So we copy the rest. We copy the rest. Again, it should be noted that this statement cannot be executed, although the whole statement has been copied correctly. The incorrect thing is what? The quotation signs. We have copied from a PDF file, so the quotation signs of the PDF file copied here will not work here in our environment. So we have to change the quotation marks, get them executed. Now, these are the only quotation marks. So largest is the is. So we can now execute this statement. Is the greatest number. Now you see, 18 is the greatest number out of these three. So it is very easy to understand the decision-making statement and very easy to understand this logic also. A conditional expression in R may either be a simple conditional expression or a compound conditional expression. A simple conditional expression or the simplest condition to be specified with if shall be of the following form. A logical value, true or false, or a logical variable containing one of these values, either true or false. An expression of the structure, variable, relational operator, or value, or any expression returning a value. It is like this one. For example, this one. This is this variable P is a variable. The P greater than Q. It is simply the of this structure. Variable, relational operator, and another variable. Variable, relational operator, another variable. That means you see variable P is variable, greater than is relational operator, Q is another variable. This is the simplest form of a condition. The conditions that we have specified in examples 3.1 and 3.2 are all simple conditions. A compound conditional expression is one which is formed by combining two or more simple conditions with the R logical operators and which is represented with double ampersand and or represented with double vertical bar. For instance, the nested if statement can be rewritten with compound conditional expressions as shown below to get the same out. So we write with these values. We copy up to this part first. That will be very easier. I think I should increase the size of this font. GUI prefers to make it better visible to you. So let me make it 20 size. Okay. So it is better visible, I think. This screen cannot be cleared with simple commands. So let me go out of this to start afresh without saving anything, and we load R again to see it afresh. So we paste here this part. And we can also change. We can also change these symbols, these quotes. I told you earlier that single quotes and double quotes have got the same meaning. So here I've used single quotes, could have been double quotes, but these quotes have been copied from a PDF file, so these quotes must be changed. Okay. Now next part, let me copy the next part of the command. Else up to this or up to this. It will be a very long command. So let me copy the rest. Copy. Paste. Now we have to change the quotes. Quotation signs here. We change it. So I think I've changed these ones earlier. Yes, I've changed these ones earlier. So now we can execute this command. Let us see what happens. R contains the largest value, 93. You see, to show you the font is very small. So let me make the font larger to 20, say. Okay. So I think now you can see it better. Now R contains the largest value, 90. P is this, Q is this, R is this. So we can also write the statement or determination of largest of three values in this way. Without writing nested P, we can write complex conditional statement using this, like this. Let us take some example, illustrative example on selection logic. Suppose a bookseller offers a discount of 18% on all books priced above rupees 500, otherwise he offers 9% discount. It is required to develop a generalized program in R to calculate the discount value and the net price of a book, and then to show them for any given price of a book. Generalized program. That means what we should not take some specific value assigned to a variable. So we should accept inputs, price of a book to calculate the discount based on the price. So price is to be accepted as input, and the statement condition will be written as we have shown earlier. So we enter printed price of a book, we give the prompt in this way, and we use the scan command to accept this value. And if we write this, if P greater than 500, discount is this, else discount is this. In a single statement, we can write. We can also write this statement beside this, as I will show you, to calculate NP. That is, discount will be calculated either using this 18% part all using this 9% part. If price is greater than 500, 18% will be the discount. Otherwise, it will be 9% of the discount, depending on the price. And you see, all these statements can be written in a single statement also, or single line also. Say enter printed price of a book. I can show you. I showed you this type of program in the last lesson also. So let us write again. We need to change these quotation marks. Why? Because they have been copied from a PDF file. Enter the printed price of a book. We want to write the next statement beside it, so you have to put semicolon. Okay. Next, we want to execute this scan command to accept the input. So we write this as it is. We copy it. As there is no quotation mark here, nothing is to be changed here. Then we next write what? This statement. If this, do the calculate D in this way, otherwise calculate D in the other way. So let me copy this also beside this. So if this, do this, else do this. Again, we want to write next statement beside. So write what? Go back to copy the next statement. NP is this. Then we can also write the next statement for showing the output. At the discount amount is rupees this and the net price is rupees this. So let us copy this also and execute this. We can write the code as I have shown here in an editor that I showed you in the lesson 2 of my lecture note. So let us change this because they have been copied from a PDF file. We have to change these quotation signs. So copying has saved my time actually, nothing else. I have made the changes. Okay. Now I can execute the statements. Now you see, it executes the first statement cat, and after that scan, enter the printed price of a book. Suppose the printed price of the book is 1,000. So it shows what? Discount is this, net price is this. I think it is very clear to you. So let us go back to see some more statements. And the program. This could also be copied there to execute in the same row. But I did not copy it because it is a very simple print statement. It is required to develop a program in R to determine the profit or loss of on a sale. So what is the task analysis here? I want to determine the algorithm of performing the task. Here we need to know the cost, C, and the sale price denoted by SP here of an item. The decision to be taken is straightforward. If the SP is greater than C, then there is a profit of SP minus C amount. Otherwise, if SP equals to C, then it will be no profit, no loss situation. Finally, if SP less than C, there will be a loss of C minus SP amount. So the required R code will be like this, and determination of profit and loss. We give a prompt here, we accept the input, we check, we accept the input, 2 inputs at a time. So they are stored where? In P1 and P2. Cost price followed by sale price. So P1 will make this will make the cost price, and P2 will make the sale price as indicated here. Accordingly, I have written the logic here. If sale price is greater than cost price, it will be a profit. Then P2 minus P1 will be the expression to be evaluated to determine the profit, and I can show the profit with this statement: profit amount is rupees this. Else, if P1 is greater than P2, there will be loss, and it can be determined by subtracting the value of P2 from P1. Then in that case, I can write in this way: the amount of loss is this. I've used here print paste, but I could have used cat also. Else it is a no profit, no loss situation. So I think these are very simple problems. I should discuss some more tougher problems. For example, it is required to develop a program to determine the roots of a quadratic equation. We know that a quadratic equation is an equation with one unknown quantity, in which the highest power of the unknown quantity is 2 and only 2. The solution of a quadratic equation involves the determination of the values of the unknown quantity, which are called its roots. As the power of the unknown quantity is 2, we shall have 2 roots as its solution. Assuming the general form of a quadratic equation to be ax square plus bx plus c equals to 0, where a, b are known constants called coefficients, and c is known constant such that a is not equals to 0. We know that the roots can be obtained by the formula x equals to minus b plus minus root over b square minus 4ac by twice a. Here b square minus 4ac is called the discriminant of the equation because it determines the nature of the roots. If its value is positive, including 0, then we get the real values of the roots. Otherwise, we get the imaginary or complex roots of the equation. The R programming language is so powerful that it can determine both real as well as imaginary roots. The process of determination of the roots has been demonstrated in the R script below. So enter the values of the coefficients. We accept the values. We prompt for the values of the coefficients A, B, and the constant C. We use the scan command to accept 3 inputs at a time, where the inputs will be stored in B1, B2 and B3. So B1 will contain the value of A in our example equation, and B2 will contain the value of B, and B3 will contain the value of C. So we write here what? B square minus 4AC. B square means B2 to the power 2 minus 4AC. The value of A is in B1 and value of C is in B3. So we have evaluated the value of the discriminant, and after evaluation of the discriminant value, we check whether the value of the discriminant is greater than 0. If it is greater than equals to 0, then we get the square root, real root, and that can be calculated by using the SQRT function available with R, and by putting the values, desired values in the equation in this solution. You see, this is the main form of the equation. So we have calculated in that way. B2 square of D, square root of D by 2. A means B1, minus B plus square root of discriminant divided by 2a, and x2 will be minus B minus square root of discriminant divided by 2a. Else, the roots will be complex. When discriminant is not greater than equals to 0, that is negative, less than 0, then roots will be complex. Then we convert the value of the discriminant into a complex number. Numeric value can be converted into complex number by using as.complex function, and we then find out the square root. Similarly, the 2 roots of the quadratic equation are then stated to be x1 and x2, and they can be shown as in this statement. Let us take another problem. It is known that a contractor pays his workers at the end of each week on the basis of the total hours worked in the week according to the following rules. For the first 35 hours, the rate of pay is fixed at rupees 19 per hour. For the next 25 hours, the rate is rupees 29 per hour. For the rest, if any, the rate is fixed at rupees 37 per hour. Moreover, no worker is permitted to work for more than 90 hours a week. It is required to devise a program in R to compute the weekly wage of the workers. Clearly, the only input requirements of the program to be written is the total hours worked by a worker in a week. Having accepted the input, we need to check whether the given input exceeds 80. If so, we terminate the program. Otherwise, we check the different conditions as per the stated rules and calculate the wage accordingly. The following R code shows the required solution. We give a prompt for this. Cat enter the hours worked in a week. Then we accept the hours worked in the variable age. Then we check if age is greater than 90. We store NA means not available, value not available in W, and age is said to be invalid. Hours is said to be invalid. And else we check if age is less than 35. If it is that, then in that case, the wage will be calculated at the rate of ₹19 per hour, and it can be obtained by multiplying the value of age by 19. If age is else means what? If age is not less than equals to 35, that means it is obviously greater than 35. So we check whether it lies within the next higher limit, which is 60. So we check whether it is less than equals to 60. In that case, for the first 35 hours, the rate will be ₹19 per hour, and we calculate by using 35, by using the expression 35 into 19. For the rest, beyond that, for the rest, that is, which is more than 35 but less than or equal to 60, can be calculated by subtracting the value of 35 from age, and that will be calculated at the rate of ₹29 per hour. Otherwise, we can calculate in this way. Why? Because for the first 35 hours, the calculation will be by using this expression 35 into 19. Else means what? It is greater than 60. So for the 60 hours, we can calculate using these two parts. This first expression is this 19 into 35 into 19. Next expression will be 35 plus 25. That is 60. So for the next 25 hours, the rate will be 29. And the expression 25 into 29 will give the wage for next 25 hours. And for the rest above 60, we can calculate it at the rate of 37. And we can find out the hours above 60 by using this formula, age minus 60. And that is to be multiplied by 37. We get the result. And we can show this in this way. Next problem is what? It is required to develop an R script to test whether a given number is even or odd. Now, it is very simple. We know that even numbers are those numbers which are divisible by 2, completely divisible. That is, divisible by 2 means what? When we divide by 2, when you divide the number by 2, the remainder it returns will be 0. Then only we can say that the number is an even number. Otherwise, we call it an odd number. So we accept input any whole number here, and we convert this whole number as into an integer, because can actually returns data in numeric form. So we convert it into integer form by using the function as.integer. And then we find out the remainder. You know that the modulo operator in R is double percentage sign. So n modulo 2, where n contains the number. If n modulo 2 equal to 0, that means what? The remainder that is obtained when n is divided by 2, if it is 0, then we can say that the number is an even number. Otherwise, we can say that the number is an odd number. I have shown this logic. I write a program in order to determine the largest one of 3 given numbers. I've already shown how to determine largest one of 3 given numbers earlier. Now, next problem is an important one to look after. Let us go through the problem. First, an electricity company installs meters having 6-digit readings at the premises of its consumers to determine the units consumed by the consumers at the end of each month by finding out the difference between two consecutive meter readings. The initial meter reading starts from 0 and accumulates units consumed until it resets after 999999, because the meters give 6-digit readings. After 999999, it will be part. It will be 000000, because in that case it will convert into next higher number, for one followed by 6 digits, which cannot be contained by the meter. So it will show after 999999 the meter will get reset. So that is to be noted. The electricity is charged according to the rules given below. For the first 50, this is the rate. For the next 75, this is the rate. For the next 125, this is the rate. For the rest, if any, this is the rate. A meter rent of rupees 25 is also added to the calculated charge to make the final bill. It is required to develop a program in R to generate the electricity bill for the consumers. Now, task analysis. It may be easily understood that each of the meters will initially show 000000. Initially, all zeros, because we have not yet started the consumption. At the end of 1 month, when the meter reading is collected, it may show a reading like this, 000175 or something like this. So it becomes easy to compute the difference between the successive meter readings by subtracting the previous reading from the current one. And that is 000175 minus 000000 gives us 175. The units consumed. As the meter is not reset to 000 after collection of meter reading at the end of each month, the consumed units get accumulated. So after 000175, the next unit, when next unit is consumed, it becomes 176. After the next unit, it becomes 177 and 7 and so on. It will go on increasing in this way. So that's why I'm telling, as the meter is not reset to 000000 after the collection of meter reading at the end of each month, the consumed units get accumulated, and at some point of time, the reading will be very near to 999999. It may be this or it may be very near to this. Hence, it may get reset to this 000000 when it accumulates 1 followed by 6 knots units, and will continue the accumulation even after automatic reset of the reading. So in framing the logic for the calculation of the units consumed by a consumer, the programmer is required to keep this concept in mind. The conditional calculations are very easy to follow. Following our script, so the solution. We accept the previous reading followed by the current reading in two variables R1 and R2, where previous reading is PR, current reading is represented with CR. We have stored R1 value in PR, R2 value in CR. Okay. Now we check whether the current reading is greater than or equals to present reading. When it is equals, no consumption is noted. When it is not, if current reading is greater than previous reading, some consumption is there, and we can calculate the units consumed by subtracting the previous reading from current reading. Otherwise, we can say that when current reading is not greater than or equals to previous reading, that is when current reading is less than previous reading, it means that the meter has been reset in the meantime, and so we have to subtract the present reading from this value to determine how many units were consumed before the reset of the meter. With that, we have to add current reading. So in this way, we get the units. Now the rest is very simple. If units less than or equals to 50, the charge is this. Else if units less than or equals to this, charge will be this. Like the previous solution, we can calculate the charge. Finally, we can, with the charge calculated, we can add 25 as the meter rent to get the final bill, and we can print it. Next problem. This is also an important problem to be considered. The registration charge of letters, parcels, etc. in the Indian post offices is calculated according to the rules described below. For the first 10 gram of part thereof, the charge is fixed at rupees 25. For next every 8 gram of part thereof, the charge is rupees 13.75, and it is applied up to a maximum total weight of 327, after which the charge is calculated for every extra gram of weight at the rate of rupees 2.75. Develop an R script to calculate the registration charge as per the rules stated. We observe that the calculation of the registration charge includes three different parts, namely when the weight lies within 10 grams, when the weight is more than 10 gram but less than or equals to 327 gram, and when the weight is more than 327. In the second part, we are required to find out the number of 8 gram intervals, keeping in mind that a fractional interval must also be treated as a full interval because of the clause part thereof. We may make use of the following formula for that calculation. Number of 8 gram intervals equals to integer part of weight in excess of first 10 grams minus 1 divided by 8 plus 1. The rest of the calculations seem to be easy for understanding. Another point is required to be noted that when the weight exceeds 327 gram, the number of 8 gram intervals is 41. For the weight in excess of the first 10 grams, the following R script shows the solution. If we accept the weight, if W is less than 10, less than or equal to 10, charge is this. So for even 1 gram weight, the charge will be 25. Else means when the weight is more than 10, then we check whether it lies within 327. If it is that, we find out the excess weight in addition to 10 grams, and we determine the number of intervals, 8 gram intervals. That can be found by using this formula, excess weight minus 1 divided by 8 as dot integer. This can also be replaced with what? With integer division operator. Excess weight minus 1 followed by integer division operator followed by 8. That will also give the result as integer, and 1 is to be added to that. So alternatively, the above statement, I have already shown it in this way. Number of intervals, EW minus 1, integer, this is the integer division operator by 8 plus 1. Then charge equals to 25 into a number of intervals into 13.75. Yes, per interval, the charge is this. Otherwise, for the first 25, for the first 10 grams, the charge is this. And for the next weights up to 327 grams, after 10, there will be 41 intervals. And those 41 intervals, the charge will be this. And for the rest, the charge will be per gram at the rate of 2.75. So the charge will be this. And now we can show the result. The rest of the problems are very simple to follow. I think, say for example, to determine whether a year is a leap year or not, you can perform what? Modulo division by 400 should be equals to 0, or that is 400. It means what? For non-sensory years, the year should be divisible by 0. So either it is divisible by 400 or it is divisible by 4 but not by 100. That is for non-sensory years, and it should be divisible by 4. For the sensory years, it should be divisible by 400. Then we can say whether it is a leap year or not. If this is true, it is a leap year, else it is not a leap year. And this is another formula to determine the number of days elapsed in between two exact dates. This is the formula for that. 1461 into function of year month by 4 plus 153 into function of month by 5 plus days. That means what? Number of days on a particular day on the starting can be calculated using this formula. So absolute difference between two dates will give the number of days elapsed in between these. So we calculate this using this. We accept the day, month, and year of the first day. Enter the day, month, and year of the later date. Enter 0 for none, and D1, and equals to 3 day, month, year. 3 values are there. Then we calculate this using this formula. Then enter the day, month, and year for the earlier date. Again, we calculate the value of n using the formula. Then we can calculate the number of elapsed days between these two days. Then comes the ternary operator, ternary form of if and the run-if statement. The ternary operator in R is if-else operator. If-else followed by parenthesis, followed by condition that is to be tested, and the expression that is to be evaluated if the condition is found to be true. Otherwise, we write the expression that is to be evaluated if the condition is false. And we can put the result of evaluation in some variable by writing in this way. Say y equals to if else x less than 5, evaluate this and put the result, return the result to y, store the result to y. If else, otherwise, if it is not true, we can check another condition. If x equals to 5, you evaluate this, otherwise evaluate this. Either if x equals to 5, we evaluate x square, otherwise we evaluate x minus 2. So x will take any one of the values. Y will take any one of the values. Either evaluation of expression x plus 2, or evaluation of x square, or evaluation of x minus 2. Next comes run-if statement. The run-if statement is used to generate a set of random numbers within a given range, excluding the values in the range. The syntax is run-if, number of randomly chosen numbers to be generated, a beginning value of the range, ending value of the range. So run-if 5 to 8 means what? We need 5 randomly selected values from the range 2 to 8. So within this range, it will show us 5 values in this way. Outcome of this lesson. Here, the learner is expected to learn the following: how to write decision-making statements with one or more alternatives, nested conditional statements, simple and compound conditional expressions, decision-making in both interactive as well as batch mode of execution, the tricks of solving some tough problems found in real-life situations, the use of ternary operators demonstrated through examples, generation of random numbers with some given condition. Thank you very much.